Subscribe to the channel so you don't miss out on any of these videos. The story of neutrinos begins in the quietest, most unassuming places in the cosmos, yet these particles have the potential to unlock some of the greatest mysteries in physics. Neutrinos, those ghostly, nearly massless particles, travel through space, and through us, largely unnoticed, emerging from some of the most dramatic and violent processes in the universe. They come from sources as diverse as the Sun, cosmic rays, supernovae, and even the Big Bang itself, carrying with them secrets about the origins, evolution, and inner workings of the universe. While neutrinos remain among the least understood particles, they may hold answers to questions that have puzzled scientists for decades. How did the universe come to be as it is today? What processes govern the cataclysmic events in deep space? And what, if anything, can neutrinos tell us about the elusive, dark sectors of the universe? For years, scientists have been driven by the challenge of detecting these particles, as neutrinos rarely interact with matter and thus evade most traditional forms of observation. Unlike other subatomic particles, neutrinos slip through nearly all barriers, including the vast, dense expanses of stars, planets, and even black holes. Each second, billions of neutrinos pass through your body without any effect, slipping by as if you weren't even there. It is this ghostly nature that has made them so elusive yet so invaluable, as their near indifference to matter allows them to travel across vast cosmic distances without being altered by the environments they pass through. As a result, neutrinos can serve as unique messengers from places in the cosmos that light itself struggles to reveal. Scientists have dedicated entire fields of study to detecting and understanding these particles, devising complex and ingenious methods to catch even a single neutrino event. Using massive underground observatories, often buried beneath thick layers of rock or ice, they search for the faintest hints of neutrino interactions. These observatories are designed to isolate the detectors from other cosmic rays and radiation, increasing the chances of capturing a neutrino's rare interaction with matter. In the ice of Antarctica, in deep mines, and in massive water tanks, scientists monitor enormous volumes of material, hoping for the faint flashes of light that signal a neutrino interaction. These flashes, though few and far between, provide essential data that researchers can analyze to learn more about the neutrino's properties and its origins. One of the most well-known sources of neutrinos is the Sun. During the process of nuclear fusion, where hydrogen atoms combine to form helium, neutrinos are produced as a byproduct. Solar neutrinos provide scientists with a unique view into the processes happening at the Sun's core, a place that is otherwise impossible to study directly. By analyzing the flux and properties of solar neutrinos, researchers can gain insights into the Sun's energy production and even verify models of nuclear fusion. Intriguingly, the study of solar neutrinos has led to some unexpected discoveries, such as the phenomenon known as neutrino oscillation, where neutrinos change types as they travel. This surprising discovery challenged previous assumptions in physics and suggested that neutrinos, once thought to be completely massless, actually possess a small amount of mass. Beyond the Sun, neutrinos are also produced in cosmic events of staggering energy, such as supernovae. When a massive star reaches the end of its life and undergoes a supernova explosion, a tremendous number of neutrinos are released in a burst that outshines the star itself. In fact, during a supernova, more energy is emitted in the form of neutrinos than in light or any other form of radiation. Detecting these neutrinos can give scientists a front-row seat to the internal mechanics of a star's death, revealing the processes that drive such powerful explosions. The detection of neutrinos from supernova 1987A, a famous supernova in the Large Magellanic Cloud, marked one of the first instances of neutrino astronomy and provided direct evidence of neutrinos' role in supernova dynamics. This event underscored the incredible potential of neutrino observation as a tool for studying some of the universe's most extreme environments. Neutrinos are also generated in high-energy cosmic rays, which are particles from space that collide with atoms in Earth's atmosphere, producing cascades of particles, including neutrinos. These cosmic ray neutrinos differ from solar or supernova neutrinos in that they carry far more energy, offering clues about the high-energy processes that produce cosmic rays. Some of these cosmic rays may come from phenomena such as active galactic nuclei or gamma-ray bursts, where particles are accelerated to near-light speeds in powerful jets from supermassive black holes or other extreme astrophysical events. Detecting neutrinos associated with these events can allow scientists to trace the origins of cosmic rays and explore some of the most powerful forces in the universe. Then, there are the so-called relic neutrinos, thought to have been produced during the Big Bang itself. These primordial neutrinos, also known as cosmic neutrino background, are extremely low-energy particles that still permeate the universe today, filling space as a remnant of the universe's fiery beginning. They provide a unique record of the universe's conditions mere seconds after the Big Bang, a time when no other observable signals were produced. Studying relic neutrinos is incredibly challenging due to their low energy and weak interaction with matter, but if detected, they could offer a glimpse into the universe's earliest moments and help answer questions about the nature of matter, energy, and the forces that shaped our cosmos. The importance of neutrinos goes beyond their role as messengers from distant or ancient cosmic events. Neutrinos have unique properties that make them crucial to our understanding of particle physics and the universe at large. For instance, the discovery of neutrino oscillation, the process by which neutrinos switch between different flavors or types as they travel, has led scientists to rethink the fundamental characteristics of neutrinos and raised questions about the mass of these particles. This discovery was groundbreaking because it contradicted the standard model of particle physics, which assumed that neutrinos were massless. Neutrino oscillation not only implies that neutrinos have mass but also opens up the possibility of interactions and forces that have yet to be understood. Furthermore, neutrinos might hold clues to the mystery of dark matter, the unseen substance that makes up a significant portion of the universe's mass. While neutrinos themselves are not thought to make up dark matter, they are among the weakly interacting particles that offer a framework for studying other elusive particles. Some theories suggest that interactions involving neutrinos or neutrino-like particles could explain aspects of dark matter, or at the very least, provide insights into the mechanisms that keep dark matter so difficult to detect. The study of neutrinos, therefore, has the potential to reveal new layers of reality, possibly pointing toward undiscovered particles or forces that lie beyond the standard model. Efforts to understand neutrinos have led to a worldwide collaboration among scientists, as detecting these elusive particles requires sophisticated technology and massive facilities. Observatories like the IceCube Neutrino Observatory in Antarctica, the Super Kamiokande in Japan, and the Sudbury Neutrino Observatory in Canada have been at the forefront of neutrino detection, using everything from Antarctic ice to massive water tanks to catch a glimpse of neutrino interactions. These observatories monitor vast volumes of matter for the rare, faint signals of neutrino collisions, which appear as tiny flashes of light caused by the interaction of a neutrino with atomic nuclei. The IceCube Observatory, in particular, has become a powerful tool for studying high-energy neutrinos. Built into a cubic kilometer of Antarctic ice, it uses thousands of sensors to detect the rare flashes of light produced when neutrinos interact with ice particles. By analyzing the direction and energy of these neutrino interactions, IceCube can trace the particles back to their cosmic sources, identifying high-energy neutrinos that may originate from black holes, gamma-ray bursts, and other extreme cosmic events. This has opened up new avenues for studying astrophysical phenomena and has allowed scientists to explore regions of the universe that would otherwise be shrouded in darkness. In addition to astrophysical sources, neutrinos may also have implications for our understanding of Earth itself. Neutrinos produced by nuclear reactions within Earth's core, known as geoneutrinos, offer a unique way to study the planet's internal structure and heat production. By detecting these neutrinos, scientists can gain insights into the processes that drive plate tectonics, volcanic activity, and the heat flow from Earth's interior. Geoneutrino studies are still in their early stages, but they represent an exciting frontier in both particle physics and geology, promising to reveal new information about the forces shaping our planet. One of the most intriguing aspects of neutrino research is the question of whether neutrinos and their antiparticles, known as antineutrinos, are in fact the same particle. This possibility is known as the Majorana hypothesis, and if proven true, it could have profound implications for our understanding of the universe. In most cases, particles and their antiparticles are distinct, with opposite charges that cause them to annihilate upon contact. However, if neutrinos are their own antiparticles, this could help explain why the universe contains more matter than antimatter, a long-standing mystery in cosmology. Detecting neutrinoless double-beta decay, a rare nuclear process, could provide evidence for the Majorana nature of neutrinos and offer clues to the matter-antimatter imbalance that allowed our universe to form. Despite the advances made in neutrino research, there remain countless unanswered questions about these particles and their role in the universe. Neutrinos defy easy categorization, inhabiting a realm of physics that lies just beyond the reach of current theories. They challenge our understanding of matter, energy, and the fundamental forces that govern the cosmos. Scientists continue to push the boundaries of technology and theory to probe deeper into the neutrinos' mysteries, knowing that each new insight into neutrinos could shift our entire understanding of the universe. Indeed, the study of neutrinos bridges several realms of physics, from the incredibly small scales of particle physics to the vast, cosmic scales of astrophysics and cosmology. This makes neutrinos a unique subject of research, as they have implications that span nearly every scale of scientific inquiry. As scientists continue to deepen their understanding, they are uncovering the remarkable ways in which neutrinos influence cosmic evolution, the formation of galaxies, and even the nature of time and space. One of the areas in which neutrinos may prove especially illuminating is in the study of extreme cosmic events, such as gamma-ray bursts, black hole mergers, and neutron-star collisions. These events release incredible amounts of energy, and often produce massive quantities of neutrinos in the process. By capturing neutrinos emitted from such high-energy phenomena, scientists hope to gain a clearer picture of what occurs within these powerful, often violent, cosmic events. This type of research is still in its infancy, but already it has begun to reveal new aspects of the universe's most energetic processes. Gamma-ray bursts, for instance, are some of the most intense energy releases in the universe, outshining entire galaxies for brief moments. The mechanisms behind gamma-ray bursts are not fully understood, but it is believed that they occur during the formation of black holes or as a result of neutron-star collisions. The detection of neutrinos from a gamma-ray burst could help scientists determine the processes driving these bursts and give clues to the environments in which they occur. Neutrinos are able to escape from regions near black holes where light cannot, providing a direct insight into these otherwise hidden parts of the universe. Black hole mergers are another significant source of neutrinos. When two black holes collide, they create a powerful disturbance in spacetime, generating gravitational waves detectable here on Earth. These mergers may also produce neutrinos, particularly if one of the black holes interacts with surrounding matter during the collision. Unlike gravitational waves, which only tell us about the masses and distances involved, neutrinos carry additional information about the physical conditions within these cataclysmic events. Observing neutrinos from a black hole merger would allow scientists to gain a fuller picture of these interactions and better understand the role of black holes in shaping the cosmos. In addition to studying high-energy events, researchers are also interested in understanding the nature of neutrino masses. The fact that neutrinos have mass, though minuscule, has profound implications. It suggests the existence of new physics beyond the Standard Model, a framework that has successfully explained many phenomena in particle physics but is incomplete when it comes to neutrinos. Theories suggest that neutrino masses could be linked to unknown particles or forces, possibly related to the Higgs boson or even dark energy. By studying the masses and oscillation patterns of neutrinos, physicists hope to identify new particles or interactions that may reveal the next layer of particle physics. The question of neutrino mass is connected to another mystery: why there is so much more matter than antimatter in the universe. In theory, the Big Bang should have produced equal amounts of matter and antimatter, which would have annihilated each other, leaving nothing behind. Yet, for reasons not fully understood, a small excess of matter survived, forming everything we see today. Neutrinos may hold the key to this asymmetry. Some scientists hypothesize that interactions involving neutrinos during the early universe could have tipped the balance in favor of matter over antimatter. If true, studying neutrinos could provide answers to one of the most fundamental questions in cosmology: why anything exists at all. Another area where neutrinos might play a transformative role is in our understanding of dark matter. Although neutrinos are unlikely to constitute dark matter, they share some properties with it, such as their weak interactions with ordinary matter and their small masses. These similarities have made neutrinos a valuable model for studying dark matter candidates, as experiments designed to detect neutrinos also offer insights into potential dark matter particles. The study of neutrinos has already inspired some of the technology used in dark matter research, and it continues to drive innovation in particle detection and analysis. Neutrinos also provide a unique opportunity to study fundamental symmetries in nature, specifically a symmetry known as CP violation, or charge parity violation. CP violation refers to processes where particles and their antiparticles behave differently, violating expected symmetries. In the case of neutrinos, certain interactions may exhibit CP violation, potentially revealing new physical principles. Detecting and measuring CP violation in neutrinos could help scientists refine their understanding of the laws governing the universe, particularly those laws that are connected to the fundamental imbalance between matter and antimatter. The pursuit of answers about neutrinos has led to numerous scientific collaborations worldwide, as no single laboratory or country can tackle this enormous challenge alone. Initiatives like the Deep Underground Neutrino Experiment, DUNE, a large international project, are working to push the boundaries of neutrino research. Located in the United States, DUNE aims to investigate several key questions about neutrinos, including their mass hierarchy, the nature of neutrino oscillation, and the possibility of CP violation. By observing neutrinos emitted from a particle accelerator, DUNE will attempt to measure these properties with unprecedented precision, adding to the global effort to map the neutrino's elusive nature. At the same time, neutrino research has spurred technological advancements that go beyond particle physics, impacting fields like medical imaging, nuclear energy, and environmental science. Neutrino detectors have inspired the development of new imaging techniques. Geoneutrino studies, for example, provide a non-invasive method to study Earth's interior, which could improve our understanding of tectonic activity and natural resources. The neutrino's role in such diverse fields highlights its importance not only to fundamental science but also to practical applications that affect our daily lives. As scientists continue their work, each neutrino detected brings us closer to understanding these elusive particles and their place in the grand scheme of the universe. Despite their ghostly nature, neutrinos carry the potential to reshape our understanding of space, time, and reality itself. By examining neutrinos, scientists are piecing together the story of the cosmos, from the fiery birth of stars to the deepest mysteries of black holes and dark matter. In this journey to uncover the secrets of neutrinos, humanity is not only exploring the universe but also probing the very fabric of existence, hoping to uncover the hidden threads that bind all things together. As researchers delve deeper into the mysteries surrounding neutrinos, one of the profound questions they aim to answer is how these particles fit into the overarching structure of the cosmos. Neutrinos are truly extraordinary in that they seem to skirt around the usual boundaries of known physics, almost as if existing between worlds. Unlike other fundamental particles, neutrinos do not strongly interact with matter or with each other, rendering them nearly invisible to traditional methods of detection. Yet, their very existence challenges and complements our understanding of the universe's formation, composition, and evolution. This interplay between invisibility and revelation is precisely what makes neutrinos one of the most fascinating objects of study in modern science. A key aspect that captivates scientists about neutrinos is their potential connection to cosmic evolution. Neutrinos were among the first particles to emerge from the early universe, shortly after the Big Bang. During this primordial era, the cosmos was a hot, dense sea of particles, with matter and antimatter constantly annihilating each other. Neutrinos, due to their weak interactions, were able to decouple from this hot plasma earlier than other particles, effectively escaping into the universe and traveling relatively unimpeded across vast distances. This makes them unique cosmic messengers, carrying information from the universe's earliest epochs. If we could decode the information embedded within these ancient neutrinos, it might provide direct insight into the moments just after the Big Bang, granting us a glimpse into the conditions that set the stage for everything that followed. The detection of such early neutrinos, sometimes called relic or primordial neutrinos, represents an immense technical challenge. They are exceedingly faint and rare, having stretched and diluted over billions of years as the universe expanded. However, scientists are currently developing techniques to try and capture these elusive relics. Some theories suggest that specialized detectors placed in exceptionally cold and isolated environments may someday be able to catch these primordial neutrinos. If successful, these efforts could yield one of the most direct windows into the Big Bang era, complementing what we've learned from cosmic microwave background radiation but with an even older perspective. Observing these relic neutrinos would help fill gaps in our understanding of how the universe expanded, cooled, and transitioned into its present state. Neutrinos also play a critical role in the life cycles of stars, particularly in the processes leading to stellar explosions. In massive stars, when nuclear fusion no longer produces sufficient energy to counterbalance the force of gravity, the star collapses under its own weight, potentially resulting in a supernova. During this collapse, neutrinos are produced in staggering numbers. In fact, a supernova releases nearly all of its energy in the form of neutrinos, rather than light or other particles. These neutrinos burst forth from the dying star, racing outward into space. For scientists, detecting these supernova neutrinos is like catching the signature of a cosmic explosion, a final farewell from a star that has completed its life cycle. The analysis of these neutrinos can provide essential information about the inner workings of stars and the physical processes leading up to and during supernovae. One of the most famous cases of supernova neutrino detection occurred with supernova 1987A, a supernova that exploded in the Large Magellanic Cloud, a neighboring galaxy. Neutrino detectors on Earth captured a brief influx of neutrinos from this supernova, marking the first time that neutrinos from an astronomical event beyond our solar system were detected. The data obtained from these neutrinos allowed scientists to verify theoretical models of supernova explosions and provided valuable insights into stellar evolution. Since then, efforts have increased to create more sensitive neutrino detectors, with the hope of capturing neutrinos from future supernovae to further understand these cataclysmic events. Another area where neutrinos are expected to play a transformative role is in mapping the structure of galaxies and galaxy clusters. Since neutrinos are capable of traversing vast cosmic distances, they can potentially reveal the distribution of matter within these colossal structures. Neutrinos interact so weakly that they are not deflected by magnetic fields, nor are they absorbed by the interstellar medium. This allows them to travel in straight lines from their source to the detector, essentially tracing a direct path through the cosmos. In theory, by capturing and analyzing neutrinos coming from different directions and distances, astronomers could develop a neutrino-based map of the universe's large-scale structure. In recent years, scientists have begun constructing neutrino observatories at an ambitious scale to better detect these particles. The IceCube Neutrino Observatory, located at the South Pole, is one of the most advanced facilities dedicated to neutrino detection. It consists of thousands of optical sensors buried deep within the Antarctic ice, capable of capturing the faint flashes of light produced when neutrinos interact with atomic nuclei in the ice. IceCube has already made significant discoveries, including the detection of high-energy neutrinos from outside our galaxy, opening up a new chapter in the study of astrophysical neutrinos. Through projects like IceCube, scientists hope to uncover the sources of cosmic neutrinos and, by extension, gain insights into the universe's most energetic processes. One particularly tantalizing source of high-energy neutrinos is thought to be active galactic nuclei, AGN, the energetic centers of galaxies that are powered by supermassive black holes. AGN emit enormous amounts of radiation across the electromagnetic spectrum, often outshining their host galaxies. It is hypothesized that AGN could be sources of high-energy neutrinos, as the intense gravitational and magnetic fields around the central black hole accelerate particles to near-light speeds, creating the conditions necessary for neutrino production. By detecting neutrinos from AGN, scientists could gain unprecedented insights into the mechanisms driving these powerful phenomena, potentially unlocking the secrets of how supermassive black holes grow and evolve. The journey of a neutrino from its origin to Earth is a cosmic voyage that often spans billions of light years, surviving encounters with countless stars, galaxies, and even clusters of galaxies. This incredible endurance gives neutrinos a unique status among cosmic messengers, allowing them to carry intact information about their birthplace and the physical conditions that generated them. Neutrinos serve as silent witnesses to some of the most dramatic events in the universe, including galaxy mergers, black hole accretion, and gamma-ray bursts. As such, they offer a way for us to observe cosmic phenomena that are otherwise hidden from traditional telescopes, providing a form of cosmic surveillance that could eventually reveal a more complete picture of the universe's most energetic and enigmatic processes. The study of neutrinos is thus not only about understanding these particles themselves but also about unraveling the grand story of the cosmos. Neutrinos could help answer some of the most profound questions about the universe. What forces shaped its evolution? What processes drive its most powerful events? And what unknown realms of physics remain hidden within the faint traces these particles leave behind? Each neutrino detection represents another piece of this cosmic puzzle, an opportunity to peer deeper into the heart of reality and perhaps uncover secrets that will reshape our understanding of space, time, and existence. As we look toward the future, there is a sense of both excitement and mystery surrounding neutrino research. The next generation of neutrino detectors promises to be even more sensitive, capable of capturing neutrinos from increasingly distant and energetic events. Projects like the proposed Hypercameo Candy in Japan aim to detect an unprecedented number of neutrinos, pushing the limits of our knowledge to new heights. These advancements could eventually lead to a neutrino-based observatory network, offering continuous, real-time monitoring of the universe's most extreme phenomena. Such a network would not only be a remarkable scientific achievement but also a testament to humanity's curiosity and drive to explore the unknown. Neutrinos are the cosmic whispers that tell the story of the universe in a language we are only just beginning to decipher. They reveal a world beyond the visible, a realm where particles dance through stars, black holes, and galaxies, unaffected by the forces that govern ordinary matter. By studying neutrinos, we are not only expanding the boundaries of science but also deepening our connection to the universe itself. These nearly invisible particles, passing silently through everything in their path, are a reminder of the profound mysteries that lie just beyond the veil of our perception, waiting to be discovered. The future of neutrino research holds incredible potential, as scientists strive to build a more complete understanding of these particles' role in the cosmic web. New and upcoming advancements in detection technology are laying the groundwork for discoveries that could redefine our grasp on fundamental physics and the universe's history. One of the most ambitious goals in neutrino science is the establishment of a global network of neutrino observatories, designed to detect these elusive particles from every corner of the universe. This vast system would effectively allow us to observe cosmic events in real time, capturing the rapid and violent processes occurring throughout galaxies and beyond. A promising development in this field is the planned construction of neutrino detectors in various extreme environments, such as in outer space or deep within the oceans. Each of these locations offers unique advantages. For instance, space-based detectors would be free from Earth's atmospheric interference, allowing them to capture neutrinos with even greater precision and range. Similarly, underwater detectors, like the KM3 project in the Mediterranean Sea, use the natural darkness and depth of the ocean to identify the rare interactions of neutrinos with atoms and water molecules. These underwater observatories complement the icy expanses of IceCube, showcasing how diverse environments enhance our ability to capture and study neutrinos from different perspectives. One of the long-term goals of neutrino research is to uncover the potential of neutrinos as tools for studying dark matter. Dark matter, an unknown form of matter that does not emit light, remains one of the greatest unsolved mysteries in astrophysics. Scientists hypothesize that neutrinos, with their weak interactions and omnipresence, could be the key to unlocking this mystery. While neutrinos themselves are not thought to constitute dark matter, their interactions, or lack thereof, could help map regions where dark matter is most densely clustered. By analyzing neutrino behavior across different cosmic regions, researchers hope to indirectly observe how dark matter shapes the structure of the universe. This ambitious objective places neutrinos at the center of efforts to solve a puzzle that has perplexed scientists for decades. Moreover, the study of neutrinos could one day provide insights into phenomena that occur within black holes. Black holes are infamous for their gravity so intense that not even light can escape their pull. This has made them extraordinarily difficult to study directly. However, it is speculated that certain types of neutrino interactions might produce high-energy particles that could escape from the edges of black holes or even from regions just beyond their event horizons. If scientists could detect neutrinos generated near black holes, they might gain unprecedented information about the processes taking place in these enigmatic objects, shedding light on one of the most extreme environments in existence. The idea that neutrinos could be the first eyes into black holes is tantalizing, opening new avenues for understanding the mysteries of gravity and space-time. In the quest to understand neutrinos, scientists are also confronting fundamental questions about particle physics itself. Neutrinos are unique among subatomic particles because they exhibit a property called flavor oscillation. This means that as neutrinos travel, they can switch between three flavors: electron, muon, and tau neutrinos. This shape-shifting behavior defies traditional expectations in physics and requires an advanced understanding of quantum mechanics to explain. The phenomenon of flavor oscillation was so groundbreaking that it led to a Nobel Prize in Physics in 2015. Yet, many aspects of this behavior remain unexplained, and ongoing research aims to discover why neutrinos behave this way and how it fits within the standard model of particle physics. The mystery of neutrino mass is another pressing issue in particle physics. For many years, scientists assumed neutrinos had no mass at all, given their elusive nature and weak interactions. However, flavor oscillation implies that neutrinos must have some mass, albeit incredibly small. The fact that neutrinos have mass challenges our understanding of how particles gain mass in the first place. The Higgs boson, famously discovered in 2012, is responsible for imparting mass to particles according to the Standard Model. Yet the masses of neutrinos are so tiny that they don't seem to fit this model entirely, suggesting there may be other mechanisms at play. Unraveling this enigma could have far-reaching implications, potentially requiring scientists to expand or revise our current theories of particle physics. Understanding neutrinos could also lead to breakthroughs in understanding the asymmetry between matter and antimatter. One of the greatest questions in cosmology is why there is more matter than antimatter in the universe. According to the Standard Model, the Big Bang should have produced equal amounts of matter and antimatter, which would have annihilated each other, leaving behind pure energy. Clearly, this is not what happened, as the observable universe is made mostly of matter. Some scientists believe that neutrinos may hold the key to understanding this imbalance. If neutrinos and antineutrinos behave differently, a phenomenon called CP violation, this asymmetry might explain why matter eventually dominated over antimatter, allowing the universe, stars, planets, and life itself to exist. The prospect of neutrinos violating CP symmetry is currently being investigated by experiments like the Deep Underground Neutrino Experiment, DUNE, in the United States. DUNE aims to shoot neutrinos across hundreds of kilometers, allowing researchers to observe how they change flavors over long distances. By studying whether neutrinos and antineutrinos oscillate differently, scientists hope to uncover signs of CP violation. If detected, this would be a monumental discovery, potentially explaining why the universe is made of matter and opening a new chapter in our understanding of cosmology. Neutrino research also holds practical implications for Earth-based technologies. Although neutrinos are typically associated with distant cosmic events, they can also be generated through human activities, such as in nuclear reactors. Scientists are exploring ways to use neutrinos to monitor nuclear reactions in real time, which could have applications in nuclear security and power generation. Since neutrinos pass undetected through most materials, they could be used to monitor nuclear reactors from a safe distance, offering a non-intrusive way to ensure compliance with nuclear agreements and safety protocols. This potential application of neutrinos science highlights how fundamental research can sometimes lead to unexpected and beneficial technologies for society. As neutrino detection technologies advance, scientists are increasingly hopeful about exploring entirely new forms of physics. Some researchers believe that neutrinos might interact with unknown particles or forces that exist outside of the standard model. Detecting these interactions would be groundbreaking, as it would open the door to a realm of new physics beyond our current understanding. This could potentially explain phenomena like dark matter or even uncover extra-spatial dimensions that lie hidden beyond our perception. Neutrinos, in this sense, could be gateways to uncovering secrets that lie beyond the known universe, effectively leading us into a new era of discovery. The journey to understand neutrinos is as much philosophical as it is scientific. At every step, neutrinos challenge our assumptions and force us to reconsider the nature of reality itself. They exist in a strange twilight zone between matter and energy, mass and masslessness, interaction and invisibility. The study of neutrinos invites us to confront the limits of human perception, reminding us that much of the universe remains hidden from our senses. Each advance in neutrino science is a reminder that reality is far more complex than we can directly observe, and that the quest for knowledge is an unending journey. As scientists push forward with their efforts to detect and understand neutrinos, they are building a bridge between the microscopic world of particle physics and the vast expanse of the cosmos. Neutrinos are the invisible threads that weave through the fabric of space and time, connecting the birth of stars, the formation of galaxies, and the evolution of the universe itself. In many ways, the study of neutrinos is like listening to a cosmic symphony, where each detected particle represents a note in a melody that stretches across billions of years. In the years to come, neutrino science may yield answers to questions that have eluded humanity for centuries. How did the universe begin? Why does it exist in its current form? And what hidden forces are at work behind the scenes? Each of these mysteries brings us closer to a deeper understanding of our place in the cosmos, and neutrinos, the most enigmatic of particles, may ultimately be the key to unlocking these profound secrets. Through each interaction, each detection, and each new insight, neutrinos whisper to us the story of the universe in a language that transcends words and images. They reveal a reality that is both vast and intimate, bridging the gap between the smallest particles and the largest structures in existence. Neutrinos, almost imperceptible yet infinitely revealing, remind us that the universe is a place of wonder and mystery, filled with truths that are yet to be discovered. The study of neutrinos has also deepened our understanding of cosmic time scales, giving us clues to the processes that shaped the universe billions of years ago. Unlike photons or other particles that may be absorbed, reflected, or otherwise altered as they travel through space, neutrinos are able to pass through almost anything without interference. This property makes them one of the most reliable messengers from the early universe, carrying information from moments just after the Big Bang to the present day. When we detect neutrinos from distant parts of the universe, it's as if we are catching whispers from an ancient time, from events and processes that otherwise left no other traces. This ability of neutrinos to act as time capsules allows scientists to peer into the distant past in a way that is unmatched by other methods. For instance, neutrinos emitted during the collapse of stars, which create supernovae, are among the earliest signals we can detect from these explosive events. Unlike the light from supernovae, which takes time to reach us and may encounter dust clouds or other obstacles, neutrinos arrive on Earth almost immediately after they are emitted, allowing scientists to gain real-time insights into stellar death. In addition, neutrinos can offer insights into some of the most energetic events in the cosmos, such as gamma-ray bursts and quasars. Gamma-ray bursts, often considered the brightest and most powerful explosions in the universe, are linked to the formation of black holes or neutron stars. These bursts produce high-energy neutrinos, which scientists believe could reveal the exact mechanisms behind these cataclysmic events. Similarly, quasars, extremely luminous cores of young galaxies powered by supermassive black holes, emit jets of particles and radiation that can generate neutrinos. Studying these high-energy neutrinos could shed light on how quasars influence the galaxies that surround them, illuminating the role of black holes in galactic evolution. As neutrino observatories expand their reach and capabilities, the prospect of creating a neutrino map of the universe becomes more plausible. This map would not only highlight regions where high-energy cosmic events are occurring but also provide a glimpse into the large-scale structure of the universe itself. Since neutrinos interact so weakly with matter, they could even allow us to observe regions obscured by dust or otherwise invisible to traditional telescopes. By combining neutrino data with observations from electromagnetic and gravitational wave astronomy, scientists could achieve a multi-messenger approach to cosmology. This integration of different types of observations allows for a more complete and nuanced picture of cosmic phenomena. One of the most fascinating implications of neutrino research is its potential to deepen our understanding of the concept of symmetry in the universe. Symmetry is a foundational principle in physics, underlying the structure of space and time, the properties of particles, and the forces that govern them. In the case of neutrinos, however, certain asymmetries emerge, such as the previously mentioned phenomenon of CP violation. CP violation in neutrinos could offer a crucial piece of the puzzle regarding why the universe consists predominantly of matter rather than antimatter, and exploring this further could have profound implications for our understanding of the fundamental forces of nature. This journey into the nature of neutrinos also has philosophical implications, as it challenges our perception of reality and pushes the boundaries of what we consider knowable. Neutrinos, with their ghostly, near undetectable presence, remind us that much of the universe operates beyond the reach of our senses. The quest to understand neutrinos reflects humanity's broader desire to comprehend the invisible and the unknown, to probe the depths of existence even when answers seem elusive. These particles invite us to grapple with questions that go beyond science, questions about the nature of existence, the limits of human understanding, and the hidden structure of reality itself. In a way, neutrinos epitomize the essence of scientific curiosity. They are both elusive and revealing, frustratingly difficult to study yet incredibly informative when captured. The pursuit of neutrinos science illustrates the lengths to which humanity is willing to go in order to uncover truth, no matter how obscure. From the depths of Antarctic ice to the vastness of space, scientists are developing new tools and methodologies to chase after particles that pass through entire planets undisturbed. This relentless pursuit exemplifies the spirit of discovery, an acknowledgement that some truths are worth pursuing, even when they lie on the edge of the unknown. The journey of neutrino science is far from over. Each breakthrough opens up new questions, each discovery unveils new mysteries. As we continue to develop more sophisticated methods of detection, as well as theoretical frameworks to explain the unique properties of neutrinos, we inch closer to answers that could reshape our understanding of the universe. The role of neutrinos in the cosmos is not merely a scientific inquiry, it is a profound exploration into the fundamental nature of reality itself. Through their quiet presence, neutrinos compel us to look deeper, to think harder, and to dream bigger. Neutrinos serve as a reminder of both the vastness of the universe and our own potential to uncover its secrets. They invite us to journey beyond the observable, to peer into the heart of creation and to recognize that the universe is a place of infinite wonder. Each neutrino, passing silently through the cosmos, carries with it a story waiting to be told, a story of stars, of galaxies, of cosmic beginnings, and of mysteries that lie beyond the grasp of ordinary perception. And in their pursuit, scientists reaffirm that there is still so much left to learn, that the quest for knowledge is unending, and that the universe, in all its depth and mystery, remains a boundless source of inspiration. The pursuit of neutrinos is truly a frontier of science that demonstrates both the incredible strides we have made and the vast realms we have yet to explore. Neutrinos are part of an intricate cosmic puzzle, a type of particle that seems almost supernatural in its behavior, unaffected by electromagnetic forces, incredibly lightweight, and seemingly indifferent to the forces that influence other particles. Their nature suggests a hidden structure to reality that does not conform to the visible, or even the immediately detectable, urging scientists to develop tools and theories as unique as the particles themselves. Our understanding of neutrinos began in the early 20th century, when physicists encountered anomalies in the conservation of energy in nuclear reactions. The apparent loss of energy suggested that there might be an invisible particle carrying away a portion of the energy. It was the genius of Wolfgang Pauli in 1930 to hypothesize the existence of this particle, which he called a neutron. However, once a larger particle was discovered and named the neutron, Pauli's particle was renamed the neutrino, or little neutral one. Pauli himself doubted we would ever be able to observe such a particle, considering its negligible interaction with other matter. Years later, the elusive nature of neutrinos became an opportunity rather than an obstacle. Scientists developed experiments that relied on massive detectors filled with materials like water or heavy water, situated deep underground to shield them from cosmic rays. By using large volumes of material, researchers hoped that a neutrino might interact with just one of the countless particles in these detectors, creating a brief flash of light or a tiny burst of energy that instruments could record. And against all odds, these experiments started yielding results, providing the first glimpses into the hidden world of neutrinos. The concept of neutrino oscillation soon emerged, transforming our understanding of these particles even further. Scientists discovered that neutrinos could switch between different flavors as they traveled through space. This was groundbreaking because it implied that neutrinos had a small, but non-zero mass, contradicting prior theories that had assumed massless particles. This discovery was revolutionary, as it not only challenged aspects of the standard model of particle physics, but also offered a new way to study the universe itself. If neutrinos oscillate based on their journey through space, then observing their behavior over vast distances could reveal new information about the cosmos they traverse. The realization that neutrinos could change flavors also opened up the study of how these transformations might occur within extreme environments, such as inside supernovae or near black holes. The oscillations depend on factors like temperature, density, and magnetic fields, which makes neutrinos sensitive to the environments from which they emerge. By studying the oscillation patterns of neutrinos from specific sources, scientists could reverse engineer the conditions of those environments, gaining insights into phenomena that are otherwise beyond human reach. One particularly exciting development in neutrino research is the construction of neutrino telescopes. These observatories are designed to capture high-energy neutrinos from distant cosmic events, with the potential to reveal insights about sources of cosmic rays, gamma-ray bursts, and even the behavior of dark matter. The IceCube Neutrino Observatory, situated at the South Pole, is one of the largest neutrino detectors in the world, consisting of thousands of sensors embedded in a cubic kilometer of Antarctic ice. By detecting flashes of light generated when neutrinos interact with ice, IceCube has captured some of the highest energy neutrinos ever observed, providing a new way to study cosmic phenomena on an unprecedented scale. One intriguing aspect of neutrino research is its potential to illuminate the nature of dark matter. Dark matter remains one of the most profound mysteries in cosmology. It doesn't emit, absorb, or reflect light, making it detectable only through its gravitational effects. However, some theories suggest that certain types of dark matter particles could decay or interact in ways that emit neutrinos. If this is the case, then high-energy neutrino observatories like IceCube could indirectly detect dark matter by observing neutrino signals that appear to originate from regions of space with high concentrations of dark matter. Though such detections remain hypothetical, the pursuit of dark matter through neutrinos represents one of the most promising frontiers in particle astrophysics. The study of neutrinos has also helped to unify our understanding of different fields of science, from particle physics to astrophysics and cosmology. Neutrinos connect phenomena on the smallest scales, like quantum interactions, to some of the largest structures in the universe, such as galaxies and clusters of galaxies. This ability to bridge scales is rare in physics, as most particles or forces apply either at the microscopic or the macroscopic level. Neutrinos, however, seem to defy this distinction, reminding us that the universe operates as an interconnected whole. The discovery of neutrinos even had implications for thermonuclear fusion, the process that powers our sun and other stars, showing that solar neutrinos could provide a direct window into the core reactions occurring within stars. One surprising revelation from neutrino science was the so-called solar neutrino problem. Early neutrino detectors, when pointed toward the Sun, observed only a third of the expected number of solar neutrinos based on theoretical models. This discrepancy confounded scientists for years until the discovery of neutrino oscillation provided the answer. As solar neutrinos travel from the Sun's core to Earth, some of them change flavors and become types that were initially undetectable. This resolved the mystery and confirmed that our theories about solar fusion were indeed accurate. The solar neutrino problem is a beautiful example of how neutrinos can challenge established scientific understanding, only to eventually reinforce it in a deeper, more comprehensive way. On Earth, neutrinos have even been studied for their potential to monitor nuclear reactors. Neutrinos are produced in large quantities by nuclear reactions, and because they travel unimpeded through most materials, they can potentially be used to track the operations of reactors in real time from a distance. This application could have significant implications for nuclear nonproliferation, allowing for new methods of ensuring that nuclear materials are used only for peaceful purposes. The development of neutrino detectors for this purpose could create a new field of neutrino diplomacy, where particle physics contributes directly to global security. As we continue to advance in our ability to detect and interpret neutrinos, the future of neutrino science seems boundless. We are just beginning to scratch the surface of what these particles can reveal about the universe. Each breakthrough, each experiment that catches a few more fleeting neutrino signals, takes us closer to answering some of the biggest questions in physics and cosmology. Neutrinos may even hold keys to phenomena we have yet to imagine, a reminder that the quest to understand the universe is not merely about gathering data or building theories, but about expanding the limits of human possibility. Ultimately, the study of neutrinos is a testament to the resilience and creativity of the human spirit. These particles, nearly undetectable and seemingly insignificant, have become one of the most exciting areas of modern science, inspiring physicists, astronomers, and philosophers alike. In their silent journey through the cosmos, neutrinos are a whisper of mysteries that lie beyond our reach but not beyond our curiosity. They challenge us to look deeper, to think more expansively, and to embrace the unknown as an essential part of discovery. As we continue to unlock the secrets of neutrinos, we are reminded that the universe, in all its vastness and complexity, is as much a frontier for imagination as it is for science. The mysteries surrounding neutrinos continue to fascinate scientists and push the boundaries of our understanding of the universe. As we unravel more about these elusive particles, we begin to realize how interconnected their role is with some of the universe's most fundamental processes. Each new discovery in neutrino physics brings us closer to understanding cosmic events that would otherwise remain hidden from view. One of the more astounding aspects of neutrino research is its potential role in uncovering phenomena related to the early universe. Neutrinos are thought to have been produced abundantly during the Big Bang, and their near-light speed and lack of interaction with other matter means that they have essentially streamed across the universe since its birth. Unlike photons, which were trapped in the dense plasma of the early universe until the epoch of recombination, about 380,000 years after the Big Bang, neutrinos escaped this plasma nearly instantly. This quality gives scientists a way to look even further back in time, to a period when the universe was less than 1 second old. These relic neutrinos are hypothesized to still exist, forming a cosmic background of low-energy neutrinos that could be detected and analyzed to learn about the conditions of the very early universe. Detecting relic neutrinos, however, remains an extraordinary challenge. Because they are so low in energy, the ability to measure them is well beyond our current technological capabilities. Nonetheless, the theory remains compelling. If we could observe these relic neutrinos, we would have access to a cosmic snapshot from an era predating the cosmic microwave background (CMB) radiation, offering insights into conditions and physics processes that are currently speculative. This concept is so promising that scientists have begun devising advanced experiments, such as those in quantum technologies, that might one day detect these low-energy particles. Should this be accomplished, relic neutrinos could become the oldest direct messengers from the universe's infancy. The role of neutrinos in supernova events is another area of intense study. When a massive star reaches the end of its life, it can explode in a supernova, releasing an incredible amount of energy and forming a neutron star or black hole. Neutrinos play a crucial role in this process. As the star's core collapses, trillions upon trillions of neutrinos are created, carrying away about 99% of the total energy released in the explosion. These neutrinos burst out from the star's core and reach Earth hours before any light from the supernova becomes visible, as the light is initially trapped within the layers of stellar material that take time to dissipate. For this reason, neutrino detectors can act as early warning systems for supernovae. Observatories like Supercameo Candy in Japan and IceCube in Antarctica monitor for sudden increases in neutrino activity that could signal a nearby supernova. If a large enough star in our galaxy were to go supernova, it would likely create a detectable surge in neutrino emissions, providing a rare opportunity to study the explosion in real time and coordinate observations across other wavelengths once the light becomes visible. This sort of multi-messenger astronomy, combining data from neutrinos, electromagnetic radiation, and even gravitational waves, represents the future of cosmic exploration. Each type of signal offers a unique piece of the puzzle, helping scientists build a complete picture of complex events like supernovae and possibly even more exotic phenomena. Neutrinos also have implications for understanding black holes and the environments surrounding them. While black holes themselves emit no light, the regions around them, such as accretion disks or jets, can produce high-energy neutrinos. When particles near a black hole are accelerated to nearly the speed of light, they can interact with surrounding material to create pions, which decay into neutrinos. Observing these neutrinos from black hole environments provides an indirect way to study the conditions around these enigmatic objects, offering clues about particle acceleration, magnetic fields, and the mechanics of the accretion process. High-energy neutrino observatories like IceCube have detected neutrinos that may have originated from regions near supermassive black holes, opening up a new method for studying these extreme cosmic structures. Even the enigma of dark energy, the force that seems to be driving the accelerated expansion of the universe, might have a connection to neutrinos. Some speculative theories propose that interactions involving very low-mass particles, like neutrinos, could contribute to the effects we attribute to dark energy. Though these ideas are still highly theoretical, they illustrate how neutrinos remain an active field for potential breakthroughs that could redefine our understanding of cosmology. By studying neutrino behavior in extreme environments or across vast cosmic distances, we could uncover new properties or forces that are currently beyond our grasp, potentially unlocking clues about dark energy or other phenomena that shape the universe on the largest scales. Neutrinos are also proving to be valuable tools in studying the structure of the Earth itself. Geoneutrinos, neutrinos emitted from radioactive decay within Earth's crust and mantle, provide insight into the processes that generate heat within our planet. This heat is responsible for geothermal phenomena, including plate tectonics, volcanic activity, and the Earth's magnetic field. By observing geoneutrinos, scientists can map regions of radioactive decay within the Earth and refine their models of heat generation and flow within the planet's interior. The study of geoneutrinos offers a non-invasive way to peer deep within Earth, a realm that is otherwise inaccessible. In the future, advancements in neutrino detection could lead to neutrino tomography, a technique that would use neutrino detectors to image the interior of Earth or other planets. Unlike seismic waves, which provide indirect information about subsurface structures, neutrino tomography could give a more direct and detailed view of internal composition. This approach might even be used on a larger cosmic scale, providing a way to study the internal structures of distant astronomical objects without direct observation. As neutrino science progresses, it also raises profound philosophical questions. Neutrinos are nearly undetectable, rarely interacting with other matter, yet they pervade the universe in unimaginable numbers. What does it mean to study something that is almost invisible to our senses and instruments? Neutrinos remind us that the universe is filled with mysteries that do not conform to human intuition. Their existence suggests that there are realms of physics we have only just begun to comprehend, governed by principles that operate on scales or within conditions beyond everyday experience. The implications of neutrinos extend beyond physics and cosmology, touching on existential questions about the nature of observation and knowledge. What does it mean to understand something we cannot directly see, feel, or experience? How much of the universe remains beyond our perception simply because we lack the tools to measure it? Neutrinos challenge us to expand our definition of what is real or observable, reminding us that much of reality may lie hidden, waiting for the right technology, theory, or moment of insight to reveal it. At its core, the study of neutrinos represents a convergence of curiosity, persistence, and creativity. These particles, though elusive, have inspired a scientific journey that spans the realms of physics, astronomy, geology, and even philosophy. The journey is far from over. With each new detector, each refined experiment, we edge closer to understanding the role neutrinos play in the grand architecture of the cosmos. In the next decade, as new observatories come online and as technology advances, we may finally begin to answer some of the most fundamental questions about neutrinos and their connection to cosmic mysteries. Perhaps we will detect relic neutrinos from the Big Bang, unlocking an era of the universe that has remained beyond our reach. Perhaps high-energy neutrino detectors will trace the origins of cosmic rays, solving a riddle that has puzzled scientists for over a century. Or perhaps new discoveries will challenge our current theories and expand the limits of what we believe to be possible. Neutrinos remind us of the vast potential for discovery that still lies before us. In a universe where so much remains unknown, they are like cosmic messengers, whispering clues about the nature of reality, encouraging us to continue exploring, questioning, and seeking answers. The story of neutrinos is not merely about particles or detectors. It is a testament to the human spirit of exploration and the never-ending quest to understand the universe we inhabit. The narrative of neutrinos is as much a testament to our scientific curiosity as it is to the boundless mysteries of the cosmos. The tiny neutrino, elusive and nearly massless, has driven humanity to create some of the most advanced technologies ever conceived, pushing our understanding of both the infinitely small and the cosmically vast. One of the most fascinating advancements in neutrino research is the development of neutrino telescopes, massive structures designed to detect the faint, rare signals of neutrinos interacting with matter. These observatories are often located in remote or unconventional locations, such as the IceCube Neutrino Observatory buried beneath the Antarctic ice or Japan's Super Kamiokande detector submerged in a deep underground mine. Such locations are chosen to shield the observatories from cosmic rays and other background radiation, isolating the delicate neutrino signals. These facilities use thousands of photomultiplier tubes and other sensitive instruments that capture the faint flashes of light, Cherenkov radiation, that occur when a neutrino collides with an atomic nucleus in the detector medium. The process of detecting neutrinos at these observatories is akin to catching a ghostly whisper amid a cacophony. For every neutrino detected, billions pass undetected, slipping through the Earth and our detectors with ease. The successful detection of neutrinos is thus a rare event, requiring enormous patience, precision, and data analysis. Yet each detection is a victory, a window into processes that could be happening billions of light years away or even within our own galaxy. In recent years, the advent of high-energy neutrino astronomy has opened new avenues for exploring the universe. IceCube, for instance, made headlines in 2013 when it detected the first high-energy cosmic neutrinos, providing direct evidence of neutrinos originating beyond our solar system. This discovery marked the beginning of a new era in astronomy, one that relies not just on light, but on particles that can traverse interstellar, and even intergalactic, distances without being absorbed or deflected. These high-energy neutrinos are suspected to originate from cataclysmic cosmic events, such as the centers of active galactic nuclei, gamma-ray bursts, and perhaps even the mysterious sources of cosmic rays, whose origins remain one of the greatest mysteries in astrophysics. Neutrinos offer a unique advantage over photons, light particles, in that they can pass through regions that would otherwise block light, such as dense clouds of gas and dust. This makes them invaluable for observing processes and environments that are otherwise invisible to traditional telescopes. For example, if a supernova or other energetic event occurs within a region obscured by dense interstellar material, it might still be possible to detect the neutrinos emitted from the event, even if no visible light reaches Earth. In this way, neutrino astronomy serves as a complement to traditional light-based astronomy, revealing hidden aspects of the universe. The detection of high-energy cosmic neutrinos has sparked excitement not only because of the potential to trace cosmic phenomena, but also because it offers a possible solution to the century-old mystery of cosmic rays. Cosmic rays, high-energy particles that bombard Earth from space, were first discovered in the early 20th century, but their origins remain unclear. While many sources of cosmic rays have been proposed, including supernovae, neutron stars, and black holes, none have been conclusively proven. Since cosmic rays are charged particles, they are deflected by magnetic fields as they travel through space, making it impossible to trace them back to their sources directly. Neutrinos, however, are unaffected by magnetic fields and travel in straight lines from their points of origin. By detecting neutrinos in tandem with cosmic rays, scientists hope to link the two phenomena, shedding light on the origins of cosmic rays and the processes that accelerate particles to near light speeds. Looking further into the future, one of the most ambitious goals in neutrino research is to create an unprecedented neutrino map of the cosmos. Such a map would provide a new form of cosmic cartography, one that captures not just the distribution of stars, galaxies, and clusters, but also the locations of high-energy phenomena and particle accelerators across the universe. This map could reveal structures or patterns that are invisible to traditional astronomy, offering a fresh perspective on the universe's architecture. Moreover, the study of neutrinos may help answer some of the deepest questions in fundamental physics, particularly in the realm of particle physics. In 2015, Takaaki Kajita and Arthur B. MacDonald received the Nobel Prize in Physics for their discovery that neutrinos oscillate between different flavors, types, as they travel. This phenomenon, known as neutrino oscillation, implies that neutrinos have a small but non-zero mass, a discovery that contradicts the predictions of the Standard Model of particle physics, which originally considered neutrinos to be massless. This surprising revelation has opened the door to a new chapter in physics, one that may require revisions or extensions to the Standard Model. Physicists are now seeking to measure the exact masses of the three known neutrino flavors, as well as to understand how neutrinos acquire their mass. There are even theories that suggest the existence of a fourth type of neutrino, known as a sterile neutrino, which would interact only through gravity and not the weak nuclear force, making it even more elusive than its already ghostly counterparts. Evidence for sterile neutrinos has been suggested in a few experiments, but it remains controversial and unconfirmed. If sterile neutrinos do exist, they could have profound implications for both particle physics and cosmology, potentially contributing to the unknown dark matter that constitutes about 27% of the universe's total mass energy content. The mystery of dark matter, in fact, is deeply intertwined with neutrino research. While neutrinos themselves cannot account for all the dark matter in the universe, they offer a window into the types of exotic particles that might make up this hidden mass. Both neutrinos and dark matter particles are weakly interacting, meaning they rarely engage with ordinary matter. This similarity has led scientists to speculate that studying neutrino interactions and properties could yield insights into the nature of dark matter, or at least provide analogies for understanding it. As we continue to investigate the neutrinos' many mysteries, we also develop new technologies that may one day allow us to manipulate or harness neutrinos in ways currently limited to science fiction. Some futurists have suggested that neutrinos could be used for communication across vast cosmic distances, given that they can pass through almost anything, including planets, stars, and galaxies, without being obstructed. This idea, though far from feasible with our present technology, exemplifies the awe-inspiring potential of neutrinos and the research surrounding them. The journey of neutrino exploration is still in its early stages, with many discoveries yet to come. Every new insight deepens our understanding of the universe, from the birth of stars to the violent death of supernovae, from the tiniest particles to the vast structures of galactic clusters. Neutrinos are indeed cosmic messengers, bearing news of distant and exotic phenomena, acting as silent witnesses to the universe's grand design. Through their study, humanity gains a foothold on mysteries that were once thought forever out of reach, each detection illuminating just a little bit more of the dark and endless cosmos. In the grand scheme of cosmic exploration, neutrinos remind us of the unseen forces and subtle connections that bind together the universe. While photons may illuminate the stars, neutrinos unveil the hidden mechanics beneath the surface, encouraging us to look deeper and to never stop questioning. The legacy of neutrino research may one day rival that of any other field, providing answers to age-old questions and sparking new ones in their wake. The study of neutrinos embodies the spirit of discovery, highlighting our relentless pursuit of understanding, no matter how invisible or elusive the truth may be. With each particle detected, we peel back another layer of the cosmos, revealing a universe far more intricate and awe-inspiring than we could have ever imagined. As we continue down the path of neutrino research, it's clear that these particles could one day serve as the keys to answering some of the most elusive mysteries in both astrophysics and fundamental particle physics. Beyond just adding layers to our understanding of cosmic phenomena, neutrinos are reshaping the way we approach the universe's deep, hidden architecture. Neutrino telescopes, for instance, aren't only expanding our observational toolkit but are also laying the groundwork for multi-messenger astronomy, a rapidly growing field that integrates data from different types of cosmic signals. Traditional astronomy relies on electromagnetic radiation, visible light, radio waves, gamma rays, to examine the cosmos. Yet, in recent years, scientists have realized that combining electromagnetic observations with data from gravitational waves and neutrinos opens entirely new windows into cosmic events. This integration enables us to study the universe in a more complete and nuanced way, where each messenger provides different insights into the processes taking place in regions far beyond our immediate reach. For example, when a neutron star merges with another neutron star, or with a black hole, the collision sends out gravitational waves, neutrinos, and photons across the universe. By analyzing these signals together, scientists can cross-reference their data, gaining insights into the mechanisms and energy scales involved in these extreme events. In 2017, the detection of gravitational waves from a neutron star merger was quickly followed by gamma-ray and optical observations. If we could also capture neutrinos from such events, we would gain an even deeper understanding of the energy dynamics, as well as the particle interactions within these violent cosmic encounters. Furthermore, neutrinos could help us answer questions about the most enigmatic forces at work on a cosmological scale, such as the origin and structure of dark energy. While dark energy is fundamentally different from dark matter and neutrinos, the techniques developed in neutrino research might eventually contribute to dark energy studies. For instance, neutrino observatories often use ultrasensitive detection methods and massive data collection systems. These techniques could be adapted to hunt for particles or anomalies associated with dark energy, providing new experimental methodologies for understanding the force driving the accelerated expansion of the universe. The study of neutrinos has also had a profound impact on our knowledge of stellar evolution and supernova dynamics. When a massive star exhausts its nuclear fuel, it can collapse under its own gravity, leading to a core collapse supernova. In the process, vast numbers of neutrinos are produced and emitted, carrying away much of the energy generated during the explosion. Observing these neutrinos allows scientists to peer directly into the core of a collapsing star, witnessing the very moments leading up to and following the explosion. This information is invaluable, as it reveals details about the mechanisms that govern supernova explosions, events that are not only visually spectacular but also crucial for seeding the universe with heavy elements. The 1987 detection of neutrinos from supernova 1987A in the Large Magellanic Cloud marked one of the first and most significant instances of observing neutrinos from a cosmic event outside the solar system. These detections confirmed several theoretical models of supernova mechanics, providing crucial insights into how supernovae evolve and disperse their elements into space. By tracking neutrinos from such events, scientists can validate predictions, improve simulations, and refine our understanding of the processes that create and distribute elements essential for life. Our ever-evolving neutrino technology holds promise for capturing similar detections in the future. Every time a supernova occurs within our galactic neighborhood, neutrino observatories stand ready to capture these fleeting particles, potentially gathering enough data to reconstruct the dynamics of the explosion itself. By listening to neutrino emissions in real time, researchers could develop a new predictive model of supernovae, estimating the timing, location, and scale of these events, giving us a fuller, more detailed perspective on the life cycle of stars. In addition to insights on distant phenomena, neutrinos also offer a rare glimpse into the inner workings of the Earth itself. The small but steady stream of geoneutrinos, emitted by radioactive decays within Earth's crust and mantle, can help scientists learn about the distribution and abundance of radioactive materials, such as uranium and thorium, in the planet's interior. Since these elements generate heat, their abundance affects geothermal energy and mantle convection, influencing volcanic activity, plate tectonics, and even the planet's magnetic field. Thus, studying geoneutrinos provides a unique, non-invasive way to probe Earth's inner layers, an opportunity that complements the information gathered from seismology. Geoneutrinos have practical applications, too. They could be instrumental in understanding the potential for geothermal energy as a sustainable resource. By mapping where geoneutrino emissions are strongest, scientists can identify regions rich in radioactive materials and thus potentially more favorable for geothermal power generation. This research represents an innovative overlap between particle physics and sustainable energy solutions, highlighting how the search for cosmic mysteries often leads to technological advancements with real-world applications. Moreover, the implications of neutrino research extend beyond the physical sciences into realms once considered purely speculative. In the field of astrobiology, for instance, researchers are exploring the role neutrinos could play in detecting biosignatures. Life, particularly microbial life, can produce unique chemical signatures in its environment. Although neutrinos do not interact directly with these signatures, studying neutrino emissions in tandem with other cosmic signals might enable us to infer the presence of chemical processes that could, in theory, indicate biological activity. This idea, though far from proven, raises intriguing possibilities for detecting life in environments with high levels of cosmic activity. For instance, some scientists speculate that the under-ice oceans of moons like Europa and Enceladus might harbor microbial ecosystems powered by geothermal heat. If these ecosystems exist, their chemical byproducts could produce secondary cosmic signals that, when paired with neutrino data, reveal hints of biological processes at work. While this is currently a speculative field of study, the potential for such interdisciplinary breakthroughs illustrates the boundless reach of neutrino research. Neutrinos also play a central role in the quest to understand the asymmetry between matter and antimatter. According to current theories, the Big Bang should have produced equal amounts of matter and antimatter, which should have annihilated each other, leaving a universe filled only with energy. Yet the observable universe is overwhelmingly composed of matter, with little antimatter in sight. This imbalance, known as baryon asymmetry, remains one of the biggest unsolved questions in cosmology. One avenue of exploration suggests that neutrinos could hold the answer. Some theoretical models propose that a particular type of neutrino, possibly a Majorana neutrino, which is its own antiparticle, could have contributed to this imbalance during the early moments of the universe. If this theory holds, it might explain why matter came to dominate over antimatter, giving rise to the galaxies, stars, planets, and ultimately, life as we know it. Detecting Majorana neutrinos or evidence of their behavior in laboratory conditions could thus provide insight into why the universe exists in its current form. The study of neutrinos continues to push the boundaries of human knowledge, merging the fields of particle physics, cosmology, geology, and even astrobiology. Each discovery reveals a new layer of understanding about our universe, demonstrating how one small particle can connect fields that once seemed disparate. As technology advances, we move closer to fully harnessing the power of neutrino observations, edging toward discoveries that could fundamentally reshape our understanding of the cosmos. The mysteries of neutrinos serve as a profound reminder of how much there is yet to uncover, a testament to the human spirit of exploration and curiosity. These nearly invisible particles, quietly traveling through the universe, carry messages from the dawn of time and the depths of the cosmos. Through them, we gain a glimpse of the processes that sculpt galaxies, shape stars, and ignite the very forces that govern existence. With every neutrino detected, we open a door into new realms of scientific inquiry, where answers to age-old questions lie just beyond our reach, urging us ever forward. The journey into the depths of neutrino research is far from over. It is, in fact, just beginning. The cosmic story they tell continues to unfold, inviting us to listen, learn, and discover, one elusive particle at a time. The profound impact of neutrinos on our understanding of the universe continues to draw the attention of scientists worldwide. These nearly massless particles provide glimpses into some of the most energetic and ancient processes, acting as elusive messengers that traverse vast distances through time and space to reach our detectors on Earth. With each detection, neutrinos are slowly revealing clues about the universe's most fundamental secrets, including the origins of cosmic rays, the properties of dark matter, and the intense environments surrounding black holes. One of the most fascinating aspects of neutrino research is the hunt for ultra-high-energy neutrinos. These are neutrinos with energies millions to billions of times greater than those produced in nuclear reactors or even most astrophysical events like supernovae. The sources of these ultra-high-energy neutrinos are still largely unknown, but scientists suspect they may originate from the most extreme phenomena in the universe, places where particles are accelerated to near light speed. Possible sources include active galactic nuclei (AGN), which are the centers of galaxies that harbor supermassive black holes, or gamma-ray bursts, which are among the brightest and most violent explosions known. If detected, ultra-high-energy neutrinos could help pinpoint the locations of these rare and exotic astrophysical objects, mapping out a neutrino sky that reveals high-energy interactions invisible to traditional telescopes. Detecting these ultra-high-energy neutrinos requires specialized detectors placed in some of the world's most remote and extreme environments. The IceCube Neutrino Observatory, located at the South Pole, has been a leader in this field. IceCube consists of thousands of sensors buried deep in the Antarctic ice, where the purity and transparency of the ice allow for the detection of tiny flashes of light produced when neutrinos interact with atomic nuclei. When a high-energy neutrino collides with ice, it creates secondary particles that emit a faint glow as they travel through the ice, a process known as Cherenkov radiation. By analyzing these light patterns, scientists can trace the path of the neutrino, determine its energy, and even estimate its origin in the cosmos. IceCube's discovery of cosmic neutrinos in 2013 marked a turning point in astrophysics, confirming that high-energy neutrinos originate from beyond our galaxy. This discovery was groundbreaking because it established neutrinos as a new kind of cosmic messenger, capable of carrying information from distant regions of the universe that were previously inaccessible. Since then, IceCube has continued to detect high-energy neutrinos, building a growing catalog of events that are helping scientists to piece together the story of the universe's most powerful accelerators. The study of neutrinos has also led to the development of innovative experimental techniques that could be used to detect other elusive particles, such as dark matter. Dark matter, which makes up about 27% of the universe, does not emit, absorb, or reflect light, making it undetectable by conventional telescopes. However, some theories suggest that dark matter particles might occasionally interact with neutrinos or produce neutrinos as byproducts of their decay. If such interactions exist, neutrino detectors could potentially serve as indirect tools for studying dark matter. The idea is that dark matter, if present in large enough quantities around galaxies, could generate neutrinos detectable on Earth. While direct dark matter interactions with neutrinos have yet to be observed, this approach remains one of the many avenues being explored in the quest to unlock the mysteries of dark matter. In this way, neutrino research could help bridge the gap between particle physics and cosmology, offering insights into the dark components of the universe that remain hidden from view. Neutrinos also carry unique information about the behavior of black holes, particularly those surrounded by accretion disks and jets. When matter spirals into a black hole, it forms an accretion disk, where temperatures soar to extreme levels, and particles are accelerated to high speeds. In some cases, these particles are ejected in powerful jets that shoot out from the black hole's poles, reaching vast distances across space. These jets are thought to be capable of accelerating particles to ultra-high energies, which could result in the production of neutrinos. Detecting neutrinos from black hole environments would offer a novel way to probe these extreme regions, providing data that is unattainable through electromagnetic observations alone. Neutrinos could reveal the inner dynamics of the accretion process, the composition of jets, and even the spin of the black hole. Since neutrinos can escape from dense regions that are otherwise opaque to light, they could act as direct probes into the heart of a black hole's gravitational influence, shedding light on one of the most enigmatic objects in the cosmos. Moreover, studying neutrinos could also yield insights into the possibility of quantum gravity effects near black holes. At the smallest scales, quantum mechanics and general relativity clash, leading to unresolved questions about the nature of space, time, and gravity. Some speculative theories suggest that neutrinos might behave differently in the intense gravitational fields near black holes, possibly displaying effects predicted by quantum gravity. While this remains an area of ongoing research, it highlights the potential for neutrino studies to contribute to our understanding of gravity at the quantum level. The idea that neutrinos could serve as quantum probes extends beyond black holes and touches upon the very fabric of spacetime itself. Certain theories propose that spacetime at the smallest scales might resemble a foamy, fluctuating structure rather than a smooth continuum. In such scenarios, neutrinos could interact with this spacetime foam in ways that alter their properties over cosmic distances. By studying how neutrinos travel across the universe, scientists may be able to gather indirect evidence of the structure of spacetime, exploring whether it conforms to our classical understanding or if it possesses hidden quantum characteristics. Neutrino research, therefore, has profound implications for both the macroscopic and microscopic realms of physics, linking phenomena that occur at vastly different scales. At the same time, it highlights the interconnectedness of all things in the universe, from the smallest subatomic particles to the largest cosmic structures. This interconnectedness is one of the most awe-inspiring aspects of neutrino physics. The idea that a particle created in the heart of a supernova millions of light-years away could travel across the cosmos and be detected on Earth, carrying with it a story about the processes that shape the universe. Another area of intense research is the role of neutrinos in understanding the origins of cosmic rays. Cosmic rays are high-energy particles that bombard Earth from all directions, but their sources remain largely unknown. The highest-energy cosmic rays are especially mysterious, as they cannot be easily explained by known astrophysical sources. Neutrinos are thought to be produced alongside cosmic rays in high-energy processes, so studying neutrinos could help scientists trace the origins of these cosmic rays. By mapping neutrino directions and energies, researchers can potentially identify the locations of cosmic ray accelerators, which could range from supernova remnants to active galactic nuclei or even more exotic sources. The mystery of cosmic rays intersects with another question: the possibility of exotic sources beyond the standard model of particle physics. While the standard model has been successful in describing most known particles and interactions, there are hints that it may be incomplete. Neutrinos, in particular, may point to new physics beyond the standard model. For instance, the phenomenon of neutrino oscillation implies that neutrinos have mass, contradicting the standard model's original predictions. This discrepancy suggests that there may be new particles or interactions awaiting discovery, particles that could explain phenomena like dark matter, dark energy, or even the nature of time itself. As we continue to refine our understanding of neutrinos, we inch closer to unlocking these mysteries, each discovery building upon the last to create a more comprehensive picture of the universe. The work being done today will lay the foundation for future generations of physicists and astronomers, who may finally be able to answer the questions that have eluded scientists for centuries. In the pursuit of neutrino research, scientists have transformed some of the most desolate and extreme environments on Earth into thriving research hubs. The South Pole, the depths of the Mediterranean Sea, and even underground laboratories shielded from cosmic rays have become the frontiers of neutrino detection. These environments allow researchers to isolate and identify neutrinos in ways that were once considered impossible, pushing the limits of technology and scientific ingenuity. Ultimately, the role of neutrinos in the universe goes far beyond their status as mere particles. They are messengers, capable of traveling vast distances through space and time, carrying with them the signatures of the most powerful and ancient forces. They are probes, allowing us to explore places where no telescope can reach, illuminating phenomena that would otherwise remain hidden. And they are mysteries in their own right, challenging our understanding of the fundamental nature of reality. The journey to understand neutrinos is a journey to understand the universe itself. It is a quest that transcends the boundaries of disciplines, linking the realms of particle physics, cosmology, astronomy, and even philosophy. As we continue to unravel the secrets of neutrinos, we are reminded of the vastness and complexity of the cosmos, a universe filled with mystery and wonder, waiting to be discovered, one particle at a time. As the investigation into neutrinos deepens, there is a growing recognition of their central importance in not just understanding the cosmos, but also in testing the very foundations of modern physics. The quest to detect and analyze neutrinos is not simply about cataloging particle interactions or observing distant cosmic events. It's also about pushing the limits of scientific knowledge, challenging established theories, and possibly uncovering entirely new areas of physics. The discovery of neutrino oscillations, which demonstrated that neutrinos have mass, provided a fundamental shift in our understanding of particle physics. Before this discovery, the standard model of particle physics had no room for massive neutrinos, meaning that their mass was assumed to be zero. The fact that neutrinos can oscillate between different types, electron, muon, and tau, implies that they must have mass, albeit incredibly small. This revelation not only opened a new chapter in particle physics but also raised questions about the potential for new particles or forces that could explain these properties. In fact, the discovery of neutrino oscillations is often considered one of the key experimental achievements of the late 20th and early 21st centuries. It was a breakthrough that defied the prevailing wisdom and sparked a wave of new research into the properties of neutrinos. The implications of these findings have been profound, leading to new experiments, new theories, and an increasing sense that neutrinos may hold the key to unlocking some of the most fundamental mysteries of the universe. One such mystery is the nature of the elusive, sterile neutrino. This hypothetical type of neutrino would not interact via the weak force, unlike the three known types of neutrinos, but could still affect the behavior of other particles. Sterile neutrinos have been suggested as a candidate for dark matter, as they could have a mass and interactions that make them detectable only through their gravitational effects. While there is currently no direct evidence for the existence of sterile neutrinos, their potential role in solving the dark matter puzzle has made them a hot topic of research. The search for sterile neutrinos is just one example of how neutrino research intersects with other unsolved mysteries in modern science. The elusive nature of dark matter, the unknown properties of dark energy, and the potential for new, undiscovered particles are all areas where neutrinos may play a crucial role. Some researchers even speculate that neutrinos could provide insights into the matter-antimatter asymmetry of the universe. Why does the universe contain far more matter than antimatter, despite the fact that both should have been created in equal amounts during the Big Bang? Neutrinos, with their unique properties, might offer a clue, possibly related to new physics beyond the standard model. As scientists develop more sophisticated detectors and refine their understanding of neutrino interactions, the potential for discovery grows exponentially. Neutrino telescopes, such as IceCube, are part of a global network of experiments designed to detect high-energy neutrinos from across the universe. These telescopes not only provide a deeper understanding of astrophysical phenomena but also allow scientists to conduct experiments that would be impossible with traditional particle accelerators or observatories. For example, detectors like the Super Kamiokande detector in Japan, a large underground neutrino observatory, have been instrumental in studying neutrino oscillations and have contributed to some of the most important discoveries in neutrino physics. Similarly, the Deep Underground Neutrino Experiment, DUNE, in the United States aims to study neutrino behavior by sending neutrino beams from Fermilab to a detector located deep underground in South Dakota. DUNE hopes to answer some of the most pressing questions in particle physics, including the nature of neutrino mass, the role of neutrinos in the evolution of the universe, and whether there are still undiscovered types of neutrinos. Another area where neutrino research could have profound implications is in the field of cosmology. By detecting neutrinos from the early universe, scientists hope to gain insights into the conditions that existed shortly after the Big Bang. Neutrinos are thought to have decoupled from the rest of the matter in the universe when the universe was just a few seconds old, and their interactions with other particles were essential in shaping the structure of the universe. The relic neutrino background, similar to the cosmic microwave background radiation, could provide a direct window into the early universe, allowing scientists to study the conditions that led to the formation of galaxies and the large-scale structure we see today. In addition to the cosmic neutrino background, scientists are also investigating the possibility of detecting neutrinos from the violent and energetic events that occur in the distant reaches of the universe. Neutrinos produced by supernovae, for instance, have been detected and provide valuable insights into the process of stellar collapse. These neutrinos carry information about the physical conditions in the core of a collapsing star and can reveal the details of the explosion that occurs when the star reaches the end of its life cycle. This information is crucial for understanding how elements are forged in stars and how the dynamics of massive stars give rise to phenomena like black holes and neutron stars. Supernova neutrinos also have the potential to help scientists test the limits of the standard model of particle physics. For example, the detection of neutrinos from a nearby supernova could provide an opportunity to study the interactions between neutrinos and other particles in unprecedented detail. These interactions could yield new insights into the properties of neutrinos, as well as the fundamental forces that govern the behavior of all matter in the universe. As we venture further into the study of neutrinos, we are also forced to confront the mystery of their origins. Neutrinos are generated in a wide variety of astrophysical processes, including the fusion reactions that power stars, the explosive collapse of massive stars into supernovae, and even the violent outflows of energy and matter from black holes and active galactic nuclei. However, despite the many known sources of neutrinos, some of the most energetic neutrinos detected in experiments remain unexplained. For example, the high-energy neutrinos detected by the IceCube Neutrino Observatory appear to originate from beyond our galaxy, suggesting that they come from some of the most distant and powerful objects in the universe. Understanding the sources of these ultra-high-energy neutrinos is a significant challenge, as they likely come from objects or phenomena that are still poorly understood. The search for their origins is one of the most exciting frontiers in neutrino astrophysics, as discovering the source of these particles could lead to groundbreaking discoveries about the most extreme environments in the universe. In addition to uncovering the origins of high-energy neutrinos, scientists are also studying the potential of neutrinos as probes for new physics. The fact that neutrinos can pass through ordinary matter almost undetected opens up exciting possibilities for using them to study hidden regions of the universe. Neutrinos could help scientists investigate the properties of dark matter, explore the structure of black holes, or even study the quantum properties of space-time itself. The study of neutrinos is thus poised to revolutionize our understanding of the universe in ways we can only begin to imagine. As detectors become more sensitive, experiments grow more refined, and our theoretical understanding continues to evolve, the role of neutrinos in solving some of the deepest mysteries of the cosmos will only become more apparent. In the end, these ghostly particles are not just a curiosity. They are key players in one of the most exciting frontiers of modern science. Neutrinos are essential for not only exploring the universe's vast, enigmatic nature but also for advancing our understanding of how the cosmos operates on the most fundamental levels. Despite their minuscule mass and the fact that they rarely interact with other matter, neutrinos are crucial in connecting many astronomical phenomena, offering insights into areas of science that were previously beyond our grasp. These elusive particles, traveling through matter unimpeded, hold the key to understanding some of the most significant and perplexing aspects of the universe. One area where neutrinos could potentially make a revolutionary impact is in the study of the cosmic microwave background, CMB. The CMB, the afterglow of the Big Bang, provides a snapshot of the universe in its infancy. This radiation offers a wealth of information about the early universe, from its temperature fluctuations to the formation of the first elements. Neutrinos, created during the Big Bang, interact with matter in ways that can leave subtle imprints on the CMB. By studying the interplay between neutrinos and the CMB, scientists could extract even more detailed information about the universe's origins and early development. In addition to their potential to reveal the universe's early moments, neutrinos are also at the heart of ongoing investigations into the nature of dark energy and dark matter. While these mysterious substances make up a vast majority of the universe's mass energy content, their properties remain largely unknown. Neutrinos, due to their unique characteristics, are considered to play an important role in these dark components. In fact, some theories propose that the existence of sterile neutrinos, hypothetical particles that do not interact via the weak force, could help explain the nature of dark matter, providing a possible connection between the known and the unknown. Furthermore, neutrinos' potential role in understanding the asymmetry between matter and antimatter is another topic of high interest. The universe is predominantly composed of matter, with very little antimatter, which poses a major puzzle in physics. Neutrinos, particularly through their interactions in extreme environments like supernovae, may hold crucial clues to understanding this imbalance. The study of neutrino interactions in such violent events could provide new insights into the processes that led to the predominance of matter over antimatter in the early universe. The role of neutrinos in supernovae is particularly intriguing. A supernova, which occurs when a massive star explodes at the end of its life, is one of the most violent and energetic events in the universe. During these explosions, neutrinos are produced in vast quantities, as the collapsing core of the star releases an enormous amount of energy. By studying the neutrinos emitted during a supernova, scientists can probe the conditions within the star's core, which are otherwise inaccessible through traditional methods of observation. This provides a unique opportunity to study the mechanisms behind these catastrophic events and gain insights into stellar evolution. The detection of neutrinos from a supernova that occurs within our galaxy would be an extraordinary event in astrophysics. The most famous example of such an observation occurred in 1987 when the supernova 1987A exploded in the Large Magellanic Cloud. Neutrinos from this explosion were detected by the Kamiokande and IMB detectors, providing scientists with a direct glimpse into the heart of a supernova for the first time. This breakthrough opened up a new avenue for studying these cosmic explosions, as neutrinos travel through matter without being absorbed, offering an unaltered view of the processes occurring within the star. More recently, the IceCube Neutrino Observatory, located at the South Pole, has been investigating high-energy neutrinos from astrophysical sources. IceCube is an enormous array of detectors embedded in the Antarctic ice sheet, designed to detect neutrinos from the most extreme and distant regions of the universe. By observing the high-energy neutrinos produced by black holes, gamma-ray bursts, and other cosmic phenomena, IceCube hopes to answer fundamental questions about the origin of these particles, the nature of the sources that produce them, and their role in the larger structure of the universe. These neutrinos, with energies far beyond those produced in particle accelerators on Earth, may hold the answers to questions that have remained unanswered for decades. One of the challenges in detecting these high-energy neutrinos is the sheer rarity of their interactions with matter. Neutrinos interact via the weak nuclear force, which is incredibly weak compared to the other fundamental forces, such as electromagnetism. This means that neutrinos can pass through light years of material, including entire planets and stars, without being absorbed or scattered. As a result, detecting these particles requires incredibly sensitive instruments capable of capturing the tiny signals that result from a neutrino interaction. The IceCube Observatory, along with other neutrino observatories around the world, represents the cutting edge of this technology, and as the sensitivity of these instruments improves, so too does our ability to uncover the secrets of the universe. Despite the challenges, neutrino astronomy is growing into a powerful tool for exploring the cosmos. Just as radio telescopes revolutionized our understanding of the universe by allowing us to observe cosmic events in a new spectrum, neutrino telescopes are opening up a new window on the universe. Neutrino astronomy has the potential to provide insights into regions of space that are invisible to conventional telescopes, such as the interiors of black holes or the early moments of the universe itself. In the next decade, advancements in neutrino detection technology are expected to revolutionize our understanding of the universe. New experiments, such as the Hypercameo Candy detector in Japan, will aim to provide more precise measurements of neutrino oscillations and further test the properties of neutrinos. These experiments could help determine whether neutrinos are their own antiparticles, a question that has profound implications for both particle physics and cosmology. Another exciting development is the potential for using neutrinos to study the properties of fundamental physics, such as quantum mechanics and gravity. Because neutrinos interact so weakly with matter, they could serve as a testbed for theories of quantum gravity, a long-sought theory that seeks to combine quantum mechanics and general relativity into a unified framework. Neutrinos' ability to travel across vast distances without interacting could offer a way to probe the structure of space-time itself, offering insights into the very nature of the universe. In addition to these fundamental questions, neutrinos are also helping to shed light on some of the most pressing mysteries of modern astrophysics. For instance, the study of neutrinos from active galactic nuclei, massive black holes surrounded by accretion disks of gas and dust, could provide a new understanding of these enigmatic objects. By studying the high-energy neutrinos emitted by the energetic processes surrounding black holes, scientists hope to unlock the secrets of these mysterious regions of space, which play a pivotal role in the evolution of galaxies and the large-scale structure of the universe. The mysteries of the universe are vast, and neutrinos are proving to be indispensable in unraveling them. As we continue to push the boundaries of our detection capabilities and deepen our theoretical understanding, neutrinos will no doubt continue to provide groundbreaking insights into the nature of space, time, and the forces that govern the cosmos. From the earliest moments of the Big Bang to the most violent explosions in distant galaxies, neutrinos are our key to unlocking the deepest secrets of the universe. Neutrinos are not just fundamental particles. They are like cosmic messengers, carrying information from places that are unreachable by light or other forms of radiation. As we continue to improve our ability to detect and study these elusive particles, we find that they hold the potential to rewrite many of our scientific assumptions. Neutrino research is helping to answer some of the most profound questions about the universe, from the nature of dark matter to the inner workings of supernovae and black holes. In fact, the study of neutrinos could even change our understanding of the very structure of the universe. As mentioned earlier, one of the most exciting areas of neutrino research involves their connection to dark matter. While the exact nature of dark matter is still a mystery, its existence is inferred from its gravitational effects on visible matter. Neutrinos, being weakly interacting particles, are candidates for dark matter, though only a specific type of neutrino, known as sterile neutrinos, could be responsible. If these hypothetical particles exist, they would have properties that make them invisible to conventional detectors. The search for sterile neutrinos is ongoing, with several experiments underway to detect them and confirm their potential role in dark matter. The interaction of neutrinos with matter could also help us understand the forces that govern the universe. The weak nuclear force, responsible for neutrino interactions, is one of the four fundamental forces of nature. Although this force is incredibly weak, it is essential for processes like nuclear fusion in stars, the decay of certain radioactive elements, and the production of elements in supernovae. By studying how neutrinos interact with other particles, scientists are learning more about the weak force and its relationship to the other fundamental forces, which could provide new insights into the nature of the universe itself. Neutrinos also have the potential to reveal new physics beyond the Standard Model, the current framework that explains most known particle interactions. One of the most intriguing possibilities is that neutrinos may violate the law of lepton number conservation, which would have profound implications for our understanding of particle physics. This concept is being tested in experiments like those that study neutrinoless double beta decay, If this rare decay process is observed, it would indicate that neutrinos are their own antiparticles, leading to a number of groundbreaking discoveries about the very nature of particles and forces. Another area where neutrinos are providing vital clues is in the study of black holes. These incredibly dense objects, with gravity so strong that even light cannot escape, have been a mystery for decades. However, neutrinos offer a potential way to study black holes indirectly. One of the most exciting recent discoveries in the field of neutrino astronomy was the detection of high-energy neutrinos that seem to originate from the vicinity of supermassive black holes. These observations suggest that black holes may not only be sources of gravitational waves and electromagnetic radiation, but also of high-energy neutrinos. By studying these neutrinos, scientists could gain new insights into the behavior of matter near black holes, including the mechanisms at play in the accretion disks and the jets that some black holes emit. The role of neutrinos in understanding gamma-ray bursts, another of the most extreme events in the universe, is equally fascinating. Gamma-ray bursts, GRBs, are powerful explosions that occur when massive stars collapse to form black holes or when neutron stars collide. These events release vast amounts of energy, often outshining entire galaxies for a brief period. Neutrinos are produced during GRBs, and by detecting them, scientists can gain a much more complete picture of these cosmic explosions. Unlike light, which can be absorbed and scattered by intervening matter, neutrinos pass through virtually everything unimpeded. This means that they can carry detailed information about the processes occurring in the heart of a GRB, information that might otherwise be hidden from view. As we explore further, the role of neutrinos in understanding the life cycle of stars remains one of the most captivating aspects of astrophysics. The production of neutrinos in stars is a crucial part of their energy production process. During the nuclear fusion reactions that occur in a star's core, neutrinos are emitted as a byproduct. These neutrinos carry away a significant portion of the energy produced in the star's core, which is essential for maintaining the star's stability. However, when stars reach the end of their lives and undergo supernova explosions, the release of neutrinos is even more significant. In fact, a supernova explosion is one of the most prolific sources of neutrinos in the universe. During a supernova, the core of the star collapses, and neutrinos are produced in such quantities that they outnumber all other forms of radiation. The explosion releases energy equivalent to the mass of the star itself, but the neutrinos carry away most of this energy, allowing the explosion to proceed. The study of these neutrinos is crucial for understanding the details of the explosion and the formation of elements, as the energy from the explosion is responsible for creating heavier elements that are later distributed throughout the universe. Neutrino detection has thus become an important tool for studying stellar evolution and the synthesis of elements in the universe. The detection of neutrinos from distant supernovae has also given rise to a new frontier in the study of cosmic distance. Supernovae are some of the brightest events in the universe, and the neutrinos they emit can travel vast distances across space without being absorbed or scattered by intervening matter. By detecting neutrinos from a supernova, scientists can measure the distance to the event more accurately than using light alone. This could revolutionize our understanding of the size and scale of the universe, allowing for more precise measurements of cosmic distances and the expansion rate of the universe itself. The ongoing efforts to detect and study neutrinos are not limited to high-energy astrophysical sources. Neutrino experiments on Earth, such as those at the Sudbury Neutrino Observatory, SNO, in Canada, are shedding light on the properties of neutrinos produced by the Sun. The study of solar neutrinos has helped solve the solar neutrino problem, a long-standing mystery about the number of neutrinos produced by the Sun. These observations confirm that the Sun produces fewer neutrinos than expected, but also revealed that neutrinos undergo a process called neutrino oscillation, where they change types as they travel through space. This discovery was a major breakthrough in our understanding of particle physics, and won the Nobel Prize in Physics in 2015. Solar neutrinos have provided a unique window into the Sun's core, allowing scientists to study the nuclear fusion processes that power the Sun. Neutrinos are produced in the Sun's core during the fusion of hydrogen atoms into helium, and their detection on Earth provides direct evidence of these processes. Unlike photons, which take thousands of years to escape the Sun's dense core, neutrinos travel straight through, providing a real-time snapshot of the Sun's inner workings. As our ability to detect solar neutrinos improves, we will gain an even deeper understanding of stellar fusion and the processes that govern the life cycles of stars. In addition to their role in astrophysics, neutrinos are also becoming an essential tool in the study of fundamental physics. As mentioned earlier, neutrinos could potentially offer insights into new physics beyond the standard model. The detection of neutrino oscillations, which shows that neutrinos have mass, has already challenged our understanding of particle physics and suggested that there are phenomena at play that we don't fully understand. The study of neutrinos may ultimately lead to a unified theory of physics, one that combines quantum mechanics with general relativity and explains the behavior of particles in extreme environments, such as black holes and the early universe. Neutrinos are some of the most intriguing and mysterious particles in the universe. Their ability to pass through matter without interacting with it makes them incredibly difficult to study, but also makes them ideal messengers for studying the most extreme and inaccessible phenomena in the cosmos. From supernovae to black holes, from the birth of the universe to the nature of dark matter, neutrinos are providing crucial clues that are revolutionizing our understanding of the universe. As our ability to detect and analyze these elusive particles improves, we can expect even more groundbreaking discoveries that will challenge our fundamental assumptions and open up new frontiers in science. The role of neutrinos in the universe is just beginning to be understood, and their mysteries will continue to captivate and inspire scientists for years to come. As we venture deeper into the study of neutrinos, we continue to uncover new and fascinating aspects of these elusive particles. The very nature of neutrinos, their interactions, and their role in the cosmos are opening up a wide range of possibilities that could fundamentally alter our understanding of the universe and the laws that govern it. One of the most exciting areas of research is the connection between neutrinos and the Big Bang. Neutrinos are thought to have been produced in enormous quantities during the first few moments after the Big Bang, when the universe was extremely hot and dense. This period, known as the neutrino decoupling, occurred about 1 second after the Big Bang. During this time, neutrinos were in thermal equilibrium with other particles, but as the universe expanded and cooled, they decoupled from the rest of the matter and began traveling freely through space. The study of these relic neutrinos, often referred to as the cosmic neutrino background, (CNB), could provide us with a snapshot of the universe from a time shortly after its birth. The detection of the cosmic neutrino background is one of the most ambitious goals in cosmology, but it remains a challenge due to the incredibly faint signals that these ancient neutrinos would produce. However, experiments like the European Space Agency's Planck mission, which is studying the cosmic microwave background (CMB), could provide indirect evidence of the CMB. The CMB itself is the afterglow of the Big Bang, and any imprints left by the neutrino background could offer valuable insights into the early universe's temperature, density, and expansion rate. By studying the cosmic neutrino background, scientists hope to learn more about the conditions that led to the formation of the universe, the nature of the early cosmos, and the processes that took place in the moments following the Big Bang. In addition to cosmology, neutrinos are playing a pivotal role in the study of particle physics and the search for new particles and forces. As previously mentioned, one of the key challenges in neutrino research is the quest to understand their mass. Neutrinos are known to have a very small mass, but exactly how small it is remains unclear. The discovery of neutrino oscillations, which showed that neutrinos can change from one type to another as they travel through space, confirmed that neutrinos have mass, a groundbreaking revelation that challenged the standard model of particle physics. This discovery has led scientists to propose new theories that could explain the origins of neutrino mass. One such theory involves the concept of the seesaw mechanism, which suggests that neutrinos obtain their mass through interactions with hypothetical, heavy particles. These interactions could involve new types of particles that exist beyond the standard model, potentially pointing to a deeper layer of physics that we have yet to discover. Experiments such as those conducted at particle accelerators, as well as the study of rare particle decays, are crucial in testing these theories and uncovering the fundamental nature of neutrinos. The mystery of neutrino mass also has profound implications for the nature of the universe itself. The weak force, which governs the interactions of neutrinos, is one of the fundamental forces in nature, and understanding how neutrinos interact with this force could lead to new insights into the relationship between the four known fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. The unification of these forces into a single theory, known as the theory of everything, is one of the holy grails of physics, and neutrinos could be the key to unlocking this ultimate understanding. As we look ahead, the development of more advanced neutrino detectors promises to open new windows into the universe. Current neutrino observatories, such as the IceCube Neutrino Observatory at the South Pole and the Super Kamiokande detector in Japan, have made significant strides in capturing high-energy neutrinos from astrophysical sources. These detectors are designed to spot the faint flashes of light that occur when neutrinos interact with matter, and they have already provided groundbreaking data on the nature of neutrinos and their sources. One of the most exciting prospects for the future of neutrino research is the detection of neutrinos from distant astrophysical events, such as gamma-ray bursts, GRBs, black hole mergers, and other extreme cosmic phenomena. By combining neutrino data with other forms of observation, such as gravitational waves and electromagnetic radiation, scientists will be able to piece together a much more complete picture of these events, offering new insights into the fundamental physics that govern the universe. Furthermore, the potential for neutrino astronomy to reveal hidden aspects of the cosmos is immense. Just as we use light to observe stars and galaxies, we could eventually use neutrinos to observe phenomena that are currently invisible to other forms of radiation. Neutrinos can pass through entire galaxies, providing a direct view of distant and obscured objects. This could allow us to study the interiors of stars, the environments around black holes, and even the deepest reaches of the universe, all with a sensitivity and precision that would be impossible with light alone. There are also ongoing efforts to develop next-generation neutrino experiments that will push the boundaries of our understanding even further. Projects like the Deep Underground Neutrino Experiment, DUNE, which aims to study neutrinos produced by a particle accelerator in the United States, will allow scientists to study neutrino oscillations in greater detail and test the properties of neutrinos with unprecedented accuracy. DUNE and other upcoming experiments will be crucial in advancing our understanding of neutrinos and their role in the cosmos, as well as their potential connections to dark matter, the fundamental forces, and the laws of physics that govern the universe. In parallel with these ambitious experimental efforts, theorists are developing new models that could explain the many unanswered questions about neutrinos. One such model is the concept of neutrino mass hierarchy, which refers to the ordering of the masses of the three types of neutrinos. The question of whether the lightest neutrino has a very small mass or whether one of the other neutrinos is the lightest is a subject of intense study. Determining the neutrino mass hierarchy is critical for understanding the particle's role in cosmology and the nature of the early universe. The answer to this question could provide valuable clues about the origins of the universe, the formation of galaxies, and the evolution of cosmic structures. Another exciting area of neutrino research lies in the study of neutrinos from supernovae. When a star undergoes a supernova explosion, it releases an enormous amount of energy, and a large fraction of this energy is carried away by neutrinos. These neutrinos can travel across vast distances, carrying information about the inner workings of the explosion and the processes that lead to the formation of heavy elements. The detection of neutrinos from a supernova is a rare event, but when it does occur, it provides a unique opportunity to study these cosmic explosions in unprecedented detail. By improving our ability to detect and analyze these neutrinos, scientists hope to gain new insights into the mechanisms that govern stellar death and the creation of the elements that make up our universe. In addition to their role in astrophysics, neutrinos are also providing important clues in the search for new particles and forces in the realm of particle physics. The study of rare particle decays, such as neutrinoless double beta decay, is opening up new possibilities for understanding the fundamental properties of neutrinos and their connections to the larger framework of the universe. These experiments are searching for signs of new physics that go beyond the standard model, and any discovery in this area could have profound implications for our understanding of the universe and the forces that govern it. The continued exploration of neutrinos is poised to reshape our understanding of the universe in profound ways. As these elusive particles continue to reveal their secrets, they will undoubtedly provide new insights into the origins and evolution of the universe, the nature of dark matter, and the very fabric of reality itself. The mysteries of neutrinos, once hidden from view, are now being slowly unraveled, offering a new frontier of exploration that will captivate scientists and enthusiasts for generations to come. As we continue to explore the intricate and fascinating world of neutrinos, it becomes clear that these particles are not only key players in the fundamental mechanics of the universe but also gateways to unlocking some of its most profound mysteries. Neutrinos are providing insights into the structure of matter, the origins of the cosmos, and even the forces that govern reality itself. The more we learn about them, the more we realize just how much there is still to discover. One of the biggest challenges and opportunities in neutrino research is understanding their interaction with other particles. As we've seen, neutrinos are incredibly elusive, interacting very weakly with matter. This weak interaction is part of why neutrinos can travel vast distances without being affected by the environments they pass through. It's also what makes neutrino detectors so sensitive and so unique. The complexity of neutrino detection lies not only in the challenge of capturing the faint signals they produce but also in the potential they hold for advancing our knowledge of fundamental physics. The extremely weak interactions of neutrinos mean that their behavior can sometimes offer clues that are obscured by more easily detectable particles. Neutrinos might reveal information about particles and forces we have yet to identify, such as hypothetical dark matter or even additional, unknown forces of nature. In this sense, neutrinos are like tiny messengers from the deep, often carrying information about parts of the universe that we cannot access in other ways. Neutrinos have long been of interest because of their potential role in answering questions related to the fate of the universe itself. The study of these particles helps scientists probe the cosmic dark ages, the time after the Big Bang but before stars and galaxies formed. During this epoch, neutrinos were already freely streaming through space, providing a record of the universe at that very early stage. They have also been essential in understanding the violent processes that drive stellar evolution, particularly in the cases of supernovae. The connection between neutrinos and supernovae has been studied extensively, and the results have been groundbreaking. When a massive star reaches the end of its life, it undergoes a catastrophic explosion that can result in a supernova. In these intense explosions, neutrinos are produced in enormous numbers. The detection of these neutrinos can provide valuable insights into the inner workings of the star and the mechanisms behind the explosion. The most famous detection of neutrinos from a supernova came in 1987 when the supernova SN 1987A exploded in the Large Magellanic Cloud. This event offered the first direct evidence of neutrinos being emitted from a supernova, and it marked a significant milestone in astrophysics. The study of supernova neutrinos has continued to evolve, with modern detectors now poised to make even more significant contributions. By analyzing neutrinos from future supernovae, scientists hope to improve our understanding of the physical processes that take place inside massive stars, including how they explode and how elements are distributed throughout the universe. Supernova neutrinos may also help solve the mystery of why some stars explode as supernovae and others do not, and whether or not certain conditions can trigger a supernova event. The cosmic impact of neutrinos is not limited to supernovae alone. The detection of neutrinos from other high-energy astrophysical events, such as gamma-ray bursts and black hole mergers, is an exciting frontier in astrophysics. Gamma-ray bursts are intense, high-energy explosions that occur in distant galaxies and are thought to be associated with the collapse of massive stars or the merging of compact objects like neutron stars. Neutrinos emitted by these bursts would offer a new way to study them, since gamma-ray bursts are often obscured by dust and gas. Neutrinos, by contrast, can pass through these materials, providing an unimpeded view of the explosion itself. Detecting neutrinos from such distant and powerful events could provide a deeper understanding of the processes that govern these extreme cosmic phenomena. Similarly, the detection of neutrinos from black hole mergers would offer invaluable information. Black holes are some of the most enigmatic objects in the universe, and their mergers, when two black holes collide, are among the most energetic events known to occur in the cosmos. Although detecting gravitational waves from such mergers has become a key area of research, neutrinos could complement this work by revealing more about the dynamics of these collisions, the properties of the black holes involved, and the fundamental nature of gravity itself. In addition to high-energy astrophysical events, neutrinos also play a key role in our understanding of the structure and evolution of the universe. Their interactions with matter can provide clues about dark matter and dark energy, two of the most elusive components of the cosmos. While dark matter cannot be observed directly, it is believed to make up about 85% of the matter in the universe. It exerts gravitational effects on visible matter but does not interact with light, making it invisible. Neutrinos, due to their weak interactions with matter, could be linked to dark matter in ways that we have yet to fully comprehend. In a similar vein, dark energy, the mysterious force that is driving the accelerated expansion of the universe, might also be related to neutrinos in some fashion. While the exact nature of dark energy remains one of the most significant unsolved problems in cosmology, researchers are exploring whether the properties of neutrinos might provide indirect evidence for the existence of dark energy, or help to explain its effects on the universe's large-scale structure. By studying neutrino emissions from distant galaxies and other cosmic objects, scientists could uncover new insights into the role dark energy plays in shaping the universe's destiny. While these grand cosmological mysteries are compelling, neutrinos are also transforming the way we think about particle physics at the smallest scales. In addition to the mysteries of neutrino mass and the search for new particles, neutrino experiments are shedding light on the fundamental forces that govern the universe. For example, the weak nuclear force, which is responsible for neutrino interactions, is one of the four known fundamental forces of nature. By studying how neutrinos interact via the weak force, scientists are gaining a deeper understanding of how this force works and how it fits into the broader framework of physics. The ultimate goal of this research is to unite the four fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, into a single theory of everything. In the quest for this grand unified theory, neutrinos are expected to play a pivotal role. In particular, the study of neutrinos may provide insights into the nature of gravity and the unification of the forces at the quantum level. One promising avenue of research involves the search for signs of quantum gravity, a theoretical framework that attempts to reconcile general relativity with quantum mechanics. Neutrinos, with their weak interactions and potential for discovering new physics, could be key to understanding how gravity behaves at the smallest scales. This could ultimately lead to a more complete and unified theory of everything, one that accounts for all the forces and particles in the universe. Moreover, the future of neutrino research promises to be shaped by advancements in technology and experimental techniques. The next generation of neutrino detectors is being designed to have unprecedented sensitivity and resolution. These detectors will enable scientists to explore new frontiers in neutrino physics, including the study of new types of neutrino interactions, the measurement of rare processes, and the search for previously unobserved neutrino sources. One particularly exciting development is the expansion of neutrino telescopes, such as the IceCube Neutrino Observatory, which has been instrumental in detecting high-energy neutrinos from astrophysical sources. The next generation of neutrino observatories will not only enhance our ability to detect these elusive particles but will also allow us to explore previously unexplored regions of the universe. With these advancements, scientists hope to detect neutrinos from the deepest reaches of space and use them to unlock the secrets of cosmic phenomena that have been hidden from view for centuries. In conclusion, neutrinos are among the most intriguing and mysterious particles in the universe. Their ability to pass through matter without interaction makes them both incredibly difficult to detect and incredibly valuable for studying the cosmos. From their role in the aftermath of the Big Bang to their potential to uncover new physics beyond the standard model, neutrinos are transforming our understanding of the universe in profound ways. As technology advances and new experiments come online, we can expect even greater discoveries, pushing the boundaries of what we know about the universe and the laws that govern it. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.